we present a novel framework that learns effective latent space for motion prior. Our agent can efficiently adapt to a variety of downstream tasks, while consistently generating smooth trajectories across the episodes. We show extreme versatility of our model in this video. We leverage conventional hierarchical control pipeline to reuse motion priors. Our model acquires continuous latent vector from the prior network and converts the posterior prior margin into a discrete latent vector. By combining these continuous and discrete latent representations, our model produces a hybrid latent representation, which can generate smooth and expressive trajectories while also maintaining the stability and training efficiency. We model the high-level policy as a discrete policy for efficient exploration. High-level policy predicts the latent margin, which is added to prior latent vector to reconstruct the final latent vector. We perform 4 experiments to demonstrate versatility of our model. Continuous model can generate unconditional motions effectively, but is not successful in downstream tasks. Discrete model is capable of performing downstream tasks, but exhibits degraded motion qualities. Our model robustly performs well in all of these scenarios, and even generates natural motions in highly underconstrained downstream tasks. We generate unconditional motion by randomly sampling from the prior distribution. Continuous model directly samples latent vector from the learned prior distribution. Discrete and our model sample an index of latent code from the uniform distribution. As seen in this video, both continuous and hybrid latent model produce high-quality motion unconditionally. However, from the quantitative comparison, we verified that our hybrid latent model generates more diverse motions compared to the continuous latent model. Unlike to the continuous or hybrid latent models, discrete latent model fails to stably generate plausible motions by random sampling from the prior distribution. As the first downstream task, we generate intermediate motions between zero-velocity keyframes. The agent with continuous latent model fails to generate natural motions, as it easily deviates from the learned motion prior during the training. While discrete latent model is able to produce natural motions during the episode, our model outperforms discrete model in terms of both naturalness and accuracy. Also, the discrete latent model shows an unstable motion when a complex keyframe setup is given. In contrast, our agent consistently produces motions with reliable qualities. As a second example, we demonstrate motion tracking with the head targets. During the training, we use a simple reward that only measures distance between a target and a head of the character. Due to the inherent limitation, continuous latent model often sacrifices motion quality in order to maximize a head tracking reward during the training. On the other hand, discrete latent model often relies on the jittering to move the body. As you can see in this sample, discrete latent model creates unnatural footsteps, while ours successfully reconstructs natural gait patterns learned from the dataset. Lastly, we train an agent to reach the target location on the ground. Similar to the previous examples, continuous model exhibits awkward motions as it fails to guarantee the naturalness without dense style reward. Unlike the continuous latent model, both discrete and hybrid latent models can generate plausible motions when reaching the target location. However, the discrete model generates undesirable jittering once it reaches the goal, as the agent isn't explicitly reinforced to take any action after arriving. Surprisingly, our agent exhibits natural idle motions as our novel architecture strongly prohibits agent to deviate motion prior. Thank you for watching.